of the Max Planck. CSIC has 120 institutes all over Spain, in all of the communities of the country, and in all branches of science. It is the third largest institution, research institution in Europe, I think behind also CNRS in France. Now, IFIC, our institute, it's also very good that we are here because you have a chance to see the town. Otherwise, if we were to hold the meeting in our standard institute headquarters, this is located in the nearby town of Paterna, you would come here rather late and so on. So this gives you a chance to see the town, but don't overdo it. Don't disperse, attend all the talks. So I should say a little bit about our institute. IFIC is one of the CSIC institutes, or one of the 120 institutes. It is the largest high-energy physics laboratory within CSIC and also in the whole country. We are involved in the main experiments, and we have also a very powerful theory department, which is very traditional. So we are a joint venture with the University of Valencia. University of Valencia is one of the two large public universities of the town. We have a total student population about 80,000. And in these universities, we have joint venture institutes which combine, they depend both on CSIC and the respective universities. So we are an example of that, which puts us in a unique advantage position because we are in an academic setting and we are a research institute with all the infrastructure associated. So I will not say much because we're already late. So enjoy the town and attend the talks. I hope that we have a very good physics during this week. I guess I should stay, right, for the first talk by Professor Ernest Ma from the University of California, Riverside. We'll be talking about neutrinos and dark matter.
Do I need the phone or, need the microphone?
It's very easy to use it.
Good morning. It's always a pleasure to come to Valencia. Jose mentioned the town. The town is very interesting. I've been here many times, and I still haven't found out a lot of interesting places. I walked around yesterday and I discovered very specialized museums of all kinds. And then the Church of St. Nicholas, of course, is fantastic. It's just nearby and you should all see it. Okay, so that is the propaganda. And now I come to my talk, which is on neutrinos and dark matter, but there's some emphasis on direct neutrinos because there's something that direct neutrinos can do for you in terms of dark matter that Majorana neutrinos cannot. And I'll come to that in a minute. So let me see here. Okay, so I will start with some basics that most people know, but maybe in a slightly different context. So concerning this connection here. And then I will talk about something that, again, many people know, but maybe again in a slightly different context. In particular, I will show that within this structure, you can define something called dark parity, which is actually identical to the dark parity that you use in supersymmetry. But again, in a slightly different context. And this is where I use the nature of the fact that neutrinos could be direct to show you that there is something that is interesting that we can do with dark matter. In fact, self-interacting dark matter. And then there are other applications. The reason for that is because Majorana neutrinos are advantageous, for example, leptogenesis. And so once you have Dirac neutrinos, you cannot do leptogenesis. So maybe there's another way, for example. So there are other applications involving the difference between Majorana and Dirac neutrinos that I'll point out. Okay, so let's go to the first thing. Okay, so this is something that everyone knows. In the SM, we don't need to have a fermion singlet because it's just not required. On the other hand, Dirac neutrino. However, this guy is a singlet, so it's not protected by any symmetry. So obviously, you can have a Majorana mass, and therefore this 2×2 mass matrix, known to every school child, is the basis of the canonical seesaw mechanism. Because if we let this mass to be much smaller than that by assumption, then we get this famous formula. Okay, so that's fine. That's how neutrinos are usually described, and they are Majorana. Okay, now we should ask the question, since this is not required in the standard model, where does it come from? And the answer is also well known, because we know about SO10. And the spinorial 16 of SO10 does contain, there are 15 guys here, and there's one extra guy there. Now, SO10 also has this virtue, which are, again, well known, because it decomposes into an SU2 left and SU2 right. And therefore, the right-handed neutrino now, which is necessary, belongs to an SU2 right doublet. So it must be there. Okay, so again, we need to break this part to the hypercharge. And the way that you do it, again, known to everyone, is by a Higgs triplet. So this guy here has a vacuum expectation value, and therefore it breaks the symmetry, it breaks this symmetry, but it also gives the right-handed neutrino a mass. So again, you get back to the canonical seesaw mechanism. Okay, so again, you have justification of Majorana instead of Dirac. So this is common law. Okay, let's deal with the B minus L more carefully here. Suppose we only look at the standard model without the singlet. Then it's well known that both B and L are conserved automatically, at least perturbatively. So the idea is that in the left-right model, this becomes a gauge symmetry, B minus L, and it's broken by this vacuum expectation value. And the answer, after you go through a little bit of work, you find out that B is still conserved, but L is now broken to -1 to the L, so left-hand parity. So this is, again, well-known law. Now, suppose I take a contrary point of view, and I want to insist that I get the Dirac neutrino. So instead of doing this, which is this object, which is must couple to this, so this has B minus L unit 2, so that it has. Suppose I get rid of this coupling. In that case, I will get a Dirac. So how do I do that? It's actually very simple. I just split it by 3 units. Okay. So this has not been recognized until recently, and there have been some model building among the audience here. So you break L by 3 units instead of 2. Okay. Then obviously you cannot, 2 doesn't go into 3, and so that is protected. And if you write down any effective interaction that tries to get a Majorana mass for right-hand neutrino, you will fail. Okay, Another option is to use the scalar doublet of 16, which breaks L by 1 unit instead of 2 or 3. Now, recall that the scalar bidoublet, which provides quarks and leptons with masses, does not break L at all. Okay? So in fact, this idea that you always take the scalar doublet of the 16 to break the symmetry was well known for 30 years in the so-called superstring-inspired E6 models, where the fundamental 27, you are only allowed to use this. So the 126 is not there. In this kind of model building, you're only allowed to use this. So it's been well known since those days that in such models, in these so-called superstring-inspired E6 models, that you must have a Dirac neutrino. There, of course, you have to assume that there's a dimension 5 operator which exists for the right-handed neutrino, which sits here, okay? And then you, of course, have VF here from this, and you can get a dimension 5 operator for it. But you have to somehow assume that it's negligible. Okay, but this is the, so it's been well known how you can get the Dirac neutrinos by the symmetry breaking, either by 1 unit or by 3 units. Okay, so now let's go down to another way of finding the right-handed neutrino. Now this is obviously going to be equivalent to what I just said before, but in a different context. It's equivalent, but in a different context. So instead of breaking it through the left-right chain, I do it with the well-known SU5, the U1 chi. Okay, and so you now know that the 16 has a 5 star and a 10 and a 1, and then the bidoublet becomes this 10, the 5 star and the 5, like this. At this point, you can already see that there's some difference between this guy and this guy. This guy, the charge under U1 chi is always odd. This one, the charge is always even. And that is where dark parity is come from later, that I'll show you. And here, just to show, to remind you that the 5 star have a SU3 triplet here, but electroweak singlet down, and you can see the lepton doublet here, and the 10 and so forth. This is all, of course, all well known. But in this context, it's easy now to single out the so-called right-handed neutrino, because it's a singlet now. It's not part of a doublet. And you can sort of manipulate with it a little bit differently. And then, of course, the two scalar doublets here are given by this. Okay. So previously, this one is mostly ignored, because if you break down to SU5, you already got all the things that you normally want anyway. So why bother with the U1 chi? So not much work has been done on the significance of U1 chi. Although there must be a gauge boson associated with it. So routinely, you search for at the LHC or any accelerator. And the current limit is 4.1. Remember, its couplings are all determined. See? Because its couplings are all determined. This 3, this so forth, this -1, and so forth. So they can easily find its decay branching fractions and everything, and so they can get this bound unambiguously, assuming that there are no extra particles that you can decay to. Okay. Now, if you go through the same discussion that we had before in the left-right case, you will find that it gives you the same thing. Okay? Allow interaction, there's the allow interaction, and so this forms a Dirac neutrino. Now, the breaking, again, by now, -10 is like 2 units, because remember this is -5 for this, so this is like, lepton number. -1, and this lepton number -2. And so again, if you do that, you get back the same answer. Okay. So the context is changed. Now, if you look at the symmetry breaking, you notice that, of course, this as well as these guys have even Q chi. So when U1 chi breaks, it breaks up because they're all even just to -1 Q chi, just as L breaks to -1 L. So this is sort of a gauge symmetry origin of this so-called R parity that has been used. Okay. Okay, so at this point, I would still like to do Dirac neutrinos. Okay. And the real reason I'll show you in another section on dark matter. Okay. Now, if I insist on Dirac neutrinos, oops, I should not use this. Remember, I should either have, instead of 2 units of lepton number, I should have 1 or 3 units. So let me use 1 unit. Okay. So now, that will work. I will have Dirac neutrinos. But the Yukawa couplings for those neutrinos must be very small. So for the same reason that the people object to Dirac neutrinos in the beginning, to say that, why is the Yukawa coupling so small? The same thing happens here. So maybe we should try a little bit harder and get a way to not to have such a small Yukawa coupling. And of course, it's well known for 30 years that you can have a seesaw scenario even for Dirac neutrinos. Okay. This has been known also long ago. However, you need a symmetry to forbid the original allow Yukawa term. That means this object, the right-handed neutrino object, must somehow has an additional symmetry which prevents it from coupling to this through this. So an example is given here. So you use this softly broken, this Z2 symmetry to forbid this dimension 4 term, which is the Yukawa coupling, this one, and this one. Now because of this minus is forbidden. Now if you maintain that this is always the case, you never get any mass for the neutrino because it would be exact. So you have to break it. And it has been well known, the trick to do this is that you break it softly. Okay, so here it is done. So this framework applies to cases where you want any kind of non-tree level Dirac neutrino mass. You must forbid that term somehow. And also applies to many models in which the Dirac neutrino mass is radiative. Okay. But I'm going to answer the question, why am I doing this? I mean, why bother with Dirac neutrino? Is there something that you can help me that Majorana neutrinos cannot? Okay, so let's go on. So in order to get the seesaw mechanism to work, instead of 3 guys, nu C and a heavy Majorana neutrino, I need 4 guys. Okay, so 1, 2, 3, 4. These 4 guys that are neutral. So I have a conjugate set, NC, which belongs to the singlet of the 126. And of course, I need both to cancel anomalies. And so under U1 chi, they would be like this. These are fermions, okay? These are fermions. So, and they are all assigned minus. Now I need one more connection. I need a singlet out of the 16, which is a scalar. This is for this one to break the symmetry, but I need one more, namely a doublet. And this doublet is just like the doublet here, but it does not belong to the 10. It belongs to 144. So its chi charge is 7. You can just look it up. This is easy. Okay? So if you do that, then there will be a coupling between nu, NC, and eta. Nu, NC, and eta. Notice they are both minus. So there will be a allow Yukawa coupling like that. Now that Yukawa coupling connects nu, NC, and eta 0. So if I can get a vacuum expectation for eta 0, then I will get a connection. But that will break the symmetry spontaneously. But in fact, there's another term which breaks the symmetry softly, and that is eta, phi, dagger, and sigma, phi, dagger, and eta. See? That means the phi dagger, this is minus 2. Minus 2, minus 5, 7. And then plus, plus, minus. That means, but it's a soft term because it's trilinear term, dimension 3. Okay, so this is what happens. So dimension 4 term must respect C2. Nu does not couple to nu C, okay? But it coupled to NC through eta 0, this term. And nu C couples to N through sigma. Oh, yeah, I did not mention that, but obviously they are all singlets, okay? N, NC, sigma, minus 10, minus 5, and minus 5 right here. Okay. Okay, so right here. So that's that term. And the sigma, this term is breaks the U1 chi symmetry. And these are allowed terms. So this is the form of a seesaw Dirac mass matrix. Okay. Now I do something else. Now I go back to Majorana, just to show you the utility of U1 chi in the Majorana case. Okay. So I'm going to tell you that dark parity is minus 1 Q chi plus 2J. And in this case, the neutrinos are actually Majorana. So you remember I already told you that all the SM fermions plus the singlet neutrino has odd charge, okay? And these all have even charge. So we can easily see that the waves will break them, but they're even, and so you just break them to minus 1 Q chi. And the residual discrete symmetry is this, which is even for all SM particles, including gauge bosons. Gauge bosons obviously have this. Now, easy step to realize that any fermion scalar with even odd U1 chi, in other words, the opposite will have and belongs to a dark sector. Okay, so this is in fact the same thing that people have been using all the time. Remember, supersymmetry essentially says is 3b plus L. And so that's equivalent to 3b minus L plus 2j. But b minus L, y, and q are related. They have to be related. This quantity is always even, because y can only be like 1/2 or 1/6, that kind of, or 1/3. And so 12y is always even. And therefore, you can see that these guys are odd. So if one is odd, the other is odd. One is even, the other is even. So it's the same, okay? So in that case, it's not something new. But the way that the phenomenology is, that implies is different. Because in one case, you only find a Z boson associated with chi. In another case, you have to find the right-handed W, so to speak, charged Ws. Okay. Now, if you say that, that this symmetry, U1 chi comes from this symmetry breaking, you mean that SU phi must be unified somehow. Okay. So you want to prove that it actually works. So, so I will skip this. I will go through this very quickly because this is the usual thing. You break the symmetry by this quantity, so you don't break U1 chi, and then this you get the SM already, and so forth, and then you use these one loop RG evolution equations, and if you have just the SM, then you will have these BC, BL, and BY, and you know that doesn't work. So you ask the question, what do I need to add? So I will add, in this case, just an example, a fermion octet, which is like this, which comes from that, and it contributes this much. A fermion triplet, which comes from that. Now, these two things are basically just the gauginos in SUSY, because that is the gluino and that is the wino. And so we know that we are mimicking what SUSY does. Up to this point, then there's a point which is not SUSY, and that is this electroweak scalar triplet, which actually comes from the 144. And the thing is that it's a triplet, but it has this -5. And it contributes that much. So all these three new additions are dark matter particles, because you can easily check that they have odd R chi. And in such a scenario, oftentimes the wino is chosen as the dark matter candidate, which has about this kind of mass. And if you put in all the other guys, you can now get a unification correctly. And because you unify these three lines, you go there and you run this back, and then you can predict the chi charge, chi coupling. Okay, so okay, I think I should go on to this. This is the punchline. Okay. Dirac neutrinos. Suppose I go back to my Dirac neutrino scenario. At that point, both baryon number B and lepton number L are conserved, even after symmetry breaking of U1 chi. Okay. Now, if I add some new particles to it, I can assign B and L appropriately by its interaction. The interaction I want will preserve B and L. Now, these assignments will lie outside U1 chi. So now it's not the marker of dark matter, but I'm now looking at B and L. So I will take this guy as before. Now, this was used to break the symmetry before in the Majorana case, but I'm in the Dirac case, so this should not break the symmetry. So the way that I can implement that is to say that this must couple to nu C because they have -5, -5. Okay, so I will assign it a lepton number -2. So this guy must not have a wave, okay, by construction. Now, so I recall that the U1 chi is broken by this, not by that. So the next step, okay, so here's the new guy that I put in. I assign it the lepton number -2. Then I put in a guy that belongs to the 16, which is like the sigma, but it has a lepton number charge assignment. So this is to distinguish it from the one that breaks the symmetry. Now, because it's a scalar, it's absolutely stable because you have L is 1, and it cannot decay into fermions, which mean decay into standard model particles, which are L is 1. So, and then this is also allowed. So it's self-interacting dark matter. So rho now plays the role of self-interacting dark matter. Now, if I also assume that this sigma is very light, then it's self-interacting dark matter. Now, so this self-interacting dark matter has been talked about for a long time, and it apparently is useful to explain the density profile of dwarf galaxies and so forth. However, there's a nagging problem. If it's a scalar, which is the case here, it must decay, and because it's not dark matter itself, it's just a mediator, and it can mix with the Higgs boson. If it's a vector gauge boson, it can mix with the U1Y gauge boson. In either case, the states you will mix and you will decay, and you will decay into electrons and photons, which are the only particles in the Standard Model that are lighter than the mediator, which is of the order of 10 MeV, let us say. But then this production at late times will be enhanced by the Sommerfeld effect, so that the decay of this will disrupt the cosmic microwave background and be inconsistent. This has been known in the last couple of years. So the elegant solution here is that sigma decays only in 2 neutrinos, because it decays into 2 Dirac neutrinos, and I mean the right-handed component of 2 Dirac neutrinos, and they are very light. So this is only example that I know that can evade this problem that about. So I'm saying, well, if there's this interaction, then what happens is, remember the dark matter couples to this too, and the Dirac neutrino now is part of the cosmic neutrino background, so there can be a drag on the because of the interaction. So perhaps you can also solve this, but I don't really know. I asked some of my friends to try to figure out whether this works or not. Okay. So other applications, I only 1 minute, so I will just go through this very quickly. And the idea is that I do not have leptogenesis anymore because lepton number is strictly conserved. But on the other hand, I could have a heavy Majorana fermion which decays to B plus minus final states. That's possible. Actually, that was also done 30 years ago, I mean, the idea. And so what happens is that what you need is this kind of structure. You have a single fermion, but you can tentatively assign it to baryon 1 because the way it couples from here. So there are two guys here. One, they are different, but they are both assigned minus 2/3 baryon number. In other words, they are scalar diquarks. And then you can also see these couplings, and you can see that they can decay into, of course you need 2 of them. So this is a complete analog of the leptogenesis, but through these diquarks, these HR diquarks. Okay. So you can also generate baryon symmetry like that.
Directly.
Yeah. And yeah, instead of using leptogenesis, you generate that, and right, okay. So you can also have I mean, out of this you can also have a color fermion octet to. This is called the Gluino solution of the. I mean, you can. This is not supersymmetry, so you can just postulate a color fermion octet and couple it to a scalar field, and you can support I mean, this is just one possibility. And this one I will skip because I run out of time. People can ask me later. And yeah, the other, I just should mention, the final answer is that Higgs can actually decay into, through the so-called fibly interacting dark matter scenario into dark matter. So, and it's called freeze in instead of freeze out, and it comes from the Higgs decay. and again through this framework. So just concluding remarks is that once you use this framework, these guys appear in a new light, and then there are several possible new insights that you can work on, and so forth. In particular, there is a case where the dark matter itself is seesaw, and then it will be triply interacting massive particle because there's a double suppression to the Higgs. So the interaction is very weak, and the only way that it can be produced is through this freezing mechanism. Okay, so I should stop here and run out. Thank you.
Okay, questions? Any question? Yes, Masi.
Yeah, so when you talk about for the decay of the Z to two neutrinos, so how much is the lifetime? Because I mean,
Not really.
because
Is
you're
it
talking about the CMB.
Yeah.
So decay to neutrinos is not as bad as photons, but still has some effect.
Yeah.
Because you're changing the gravitational potential and all that stuff.
Yeah, you're right. I did not go into that's adjustable. What you mentioned, in other words, that coupling is not involved in determining self-interacting dark matter. So that coupling is adjustable. I put in some random coupling, and I get 10 to the minus 7 seconds. Now that number can be changed. So experts like you can figure out what is the actual limit on that. Yeah, but I put in some. I get 10 to minus. This is a sample number.
Thanks.
Any more questions? Yes.
Have you considered the possibility of implementing in this framework this neutrino genesis, Dirac leptogenesis that was actually proposed like 20 years by Michael Ratten?
No, I did not, but I understand what you mean. In that case, I think you have to go back to the non-seesaw scenario where the Yukawa coupling is actually very, very small. I mean, you can do that. I mean, but yeah, that would be a argument for very, very small Yukawa couplings. But I decided to do a seesaw, and so that option is not there anymore. So I use the decay into baryon, to postulate a particle that can decay into baryon, anti-baryon to do that same thing. Yeah.
So one last question. Mike?
Stupid question. I mean, what does this E6 and so on give you except for these discrete symmetries? So I mean, put it differently, if you have such an E6 or so, you have all sorts of problems like doublet triplet splitting, all sorts of exotics that float around. Yeah, well, how do you do? I don't do actually. I'm not doing E6, right? Because I only pointed out that E6 was considered in those days in those days, and the short answer to that is that in all those models the neutrino mass is Dirac, and then later on I only use SO10 basically. So but I mean it's only that you look for anomaly-free discrete symmetries and use this Ibanez-Ross result that this has somehow, if it does become SO10 and it comes to E6 or something like this. Is that what you are doing? I mean, where you had this E6 discussion in the beginning, what is in all of this? No, the E6 part is just only to remind you that that in the context of E6, because in those days, because you are only allowed to use the 27 of E6. I mean, for model building purposes, you're only allowed to use 27, and 27 has 16, 10, and 1. It has no 126. That's all I was saying. Yes. Okay. And there's a 351. Yes. Yeah, all right.
Okay, so let's thank Ernest for a very nice. Second speaker is David Sardenio on dark matter. No. Right? No,
I'm not talking about dark matter.
not dark matter.
No,
You change their identity.
I haven't changed anything.
Neutrino physics with direct dark matter. Come on, here's dark matter. Direct dark matter detection experiments.
I think just to confuse Jose and just to also make the connection with the talk by Professor Ma before, I'm going to be talking about neutrino physics, but the connection with dark matter here comes from the fact that I will try to detect new physics in the neutrino sector using dark matter experiments, all right? So that's the only connection that's going to be. So I think I have one slide that mentions dark matter and nothing else. I hope that that's fine. Right, okay, so this whole talk is based on a series of works that I've done with a number of collaborators, among which I would like to stress out the role of my PhD student, Elliot Reed, especially in the last work, and then also in collaboration with Malcolm Fairburn, Aaron Vincent, Salim Bohm, Pedro Machado, and a number of other people. This is my only slide on dark matter. We've been looking for dark matter, and in particular the so-called weakly interacting massive particles, already for many years. And we've constructed some underground experiments which excel at looking for very rare phenomena. Okay? The idea behind what we call direct dark matter detection is the following. We've got dark matter particle that comes from the dark matter halo around us that would scatter off nuclei or electrons in these underground experiments, and therefore the signal that we're looking for is kind of rare scattering in a very, very quiet environment. We can look either for electronic recoils, as I say here, which are mostly sensitive. These are super interesting because they are very sensitive to very light dark matter. But we also have nuclear recoils, and this is mainly or one of the main signals we're looking for, which are able to look for elastic or inelastic scattering of the so-called weakly interacting massive particles in a range of energies of the order of the kilo-electron volt, but also, in principle, again, sensitive to masses above 1 GeV all the way to multi-TeV. These experiments have become excellent. I'm working with Super CDMS, and that's one of the best experiments. I'm not finding dark matter yet. But this also means that these are excellent to also look for rare phenomena that might happen through very similar processes. In particular, there's one of these rare phenomena that we might be able to test in the coming future. And this is due to the so-called coherent scattering of neutrinos of nuclei. Okay? The reason for this is the following. When you calculate the equivalent wavelength of neutrinos, especially solar neutrinos, this is essentially the same as the nuclear size. So the same argument behind WIMP scattering follows here, which is that these neutrinos can scatter coherently with the whole nucleus. Now, if you go back to my signals here, what you realize is that this same process can actually be due to solar neutrinos and through standard model physics, which is quite cool. It was also quite cool because it was thought at some time that direct detection experiments would be among the first one to observe this phenomena, but as you know, the coherent collaboration has observed this already with spallation sources. Okay? The cross-section is extremely small. We're talking about electroweak interacting particles anyway. It's only within the reach of ultra-low background experiments. And I mean, so far here is not mysterious. This is just, again, a standard model process. The main worry for dark matter experiments is that this is a background that is in principle very, very difficult to reduce. Okay, and this is how, for example, in the language of direct detection experiments, we call this the neutrino floor. What I'm going to argue in my talk, however, is that we can actually use this neutrino floor to extract some properties. First of all, try to probe some solar properties, which I think is very interesting, and also it can allow us to probe new physics in the neutrino sector. So just to recap a little bit, how do we detect neutrinos in a direct detection experiment? And in principle, as you see, there are two possibilities here. Again, similar to how we're looking for dark matter, we can either look for scatterings of electrons or scatterings of nuclei, or if you want to see at a more fundamental level, scatterings of quarks. Okay? Scatterings of electrons can proceed through either neutral or charged currents, as you can see here, exchange of a Z or a W boson. And if you're looking for a scattering of quarks, then essentially we're only left with a neutral current here. Again, when you're looking for the whole coherent scattering here with the whole nucleus, what you would do would be promoting the fundamental scattering cross-section of quarks to construct the scattering cross-sections of protons and neutrons, and then to consider the whole coherent wavelength with the whole nuclei. Okay, so in a very, very similar manner as you do with, as you would do with dark matter. Okay. Say again, sorry.
For coherent scattering, you need vector count.
In this case, it would be, yeah. Again, we're talking here so far only standard model, all right? But you can also add new couplings if you wanted to. So again, starting with only the standard model cross-sections, you can actually sit down and calculate those. It's very easy. The neutrino electron scattering is just, it just reads here from the different couplings, the vector and axial couplings of the electrons and neutrinos. Again, you have different contributions for the different types of neutrinos, and also it depends on whether you're scattering of electrons, muon, or taus, okay? But we know how to calculate that easily. The coherent neutrinos nucleus scattering also follows from the same principles, and the only thing that you gain here is a form factor that parameterizes the loss of coherence if you're scattering at higher energies. But again, it's the same form factor. You can use Helm, for example, same form factor that you would encounter for WIMP scattering. The way to calculate the total rate in these kind of experiments is you just take the neutrino flux, the scattering cross-section, integrate it for the range of energies that your experiment can have access to, and then you've got a differential rate that I will show now in a minute. And the interesting thing here for us is, again, that, all of this is known. Okay, so the only thing that we have to do is integrate for the total neutrino fluxes, and this is just a collection of the fluxes that we are considering in this work. Okay, so starting from low energies all the way up to high energies, what you find on the left-hand side of the plot are the low energetic PP neutrinos, which are very numerous, obviously, and if your experiment can have access to those, then these are actually going to dominate the total flux. As you increase in energy, you find the so-called CNO neutrinos, which are here in blue, and they come from a different cycle of production in the sun. Boronate neutrinos, which are the most energetic neutrinos we can get from the sun, and then you transition onto atmospheric neutrinos, okay? We also have a population of diffuse supernovae background that comes from the explosion of supernovae in the cosmos. Okay, there's some uncertainty in those, and unfortunately, this population of neutrinos just happens to be in the transition from solar neutrinos to atmospheric neutrinos, so it's quite challenging actually to observe those. Right, again, taking these flux of neutrinos, you can try to see how what the predicted rate in direct detection experiments would be. And I'm plotting this one here. I'm borrowing this plot from a paper by Tali, Figueroa, Feliciano, and collaborators in 2014. This is as a function of the recoil energy with nuclei. This is assuming coherent nuclear scattering, the number of events per ton per year per keV. And all of these come from the different population of solar neutrinos, again, at very low recoil energies. If you're a theorist, you're allowed to do that. If you're an experimentalist, you might worry that I'm plotting here scattering recoil energies, probably of the order of the electron volt. Okay? PP neutrinos would be here. CNO neutrinos are somewhere around here. Is this little bump that you can see here at energies below keV. Boronate neutrinos are by far the easier to observe. If you're familiar with direct detection experiments, you know that the typical threshold for these experiments is around keV, 2 keV, 10 keV or so. And then atmospheric neutrinos just lie very, very low. You see here that there are 6 orders of magnitude difference. Now, this is great news if you were looking for neutrinos. If you're looking for dark matter, your main problem is this, is that a 6 GeV WIMP with a given cross-section has exactly the same signature as boronate neutrinos. And that is mainly what has been worrying people in the direct detection community for the last couple of years. There's a second worry. If your experiment is sensitive to heavier neutrinos, then you may also worry that 100 GeV WIMPs also look exactly like atmospheric neutrinos, all right? So these are 2 signals that are going to be difficult to disentangle in the near future, and that's actually quite interesting as well. This has also given, has also been given the name of a neutrino floor, which is essentially this orange line that you plot on the sensitivity plot for direct detection experiments. So just to recap, this is the scattering cross-section for WIMPs as a function of the WIMP mass. So this is a dark matter plot. I think I lied. This is my second dark matter plot. And these are the sensitivities of some of the experiments. This plot is not updated. LUX has currently increased. LUX, Xenon 1 ton, and Panda X have currently increased their sensitivity by about an order of magnitude in this plot. What I wanted to emphasize, however, is that this orange line, or this orange or yellow area, is where you start seeing neutrinos with your direct detection experiment. Okay? So in principle, if you found a dark matter signature that falls below the neutrino floor, your main worry is that that might actually be due to neutrinos and not dark matter at all. Okay? Now, so we wonder actually to what extent we could use that signal with direct detection experiments. And just to come back very briefly to the two possible ways of detecting them, I just wanted to emphasize that if you're looking for electron recoils or neutrino recoils, you're actually exploring very different populations of the neutrino flux, simply because the momentum exchange is sensitive to the mass of the object that you are scattering off. Okay? So if you're scattering off quarks, in order to have a recoil energy of the same in the observable range, you need a larger momentum. If you're scattering off electrons, in principle, you need a smaller momentum to produce the same recoil energy. This is simply kinematics. So this means that in my usual plot of neutrino fluxes, again, just the PP neutrinos, boron-8 neutrinos, and in blue, I'm showing the CNO neutrinos, neutrinos from the CNO cycle. It means that if you're looking for nuclear recoils, typically, I don't know if you can see here the different shading in these colors. This means for a future neon experiment, argon experiment, xenon experiment, germanium, the dark color is showing you more or less which is the population of neutrinos that you can probe with nuclear scattering, sorry, with nuclear recoils. Okay, so you can see, for example, that xenon experiments with a threshold of about 2 kiloelectron volts might be able to probe the population of boron-8 neutrinos. This is something that they're actually looking forward to doing, and this is actually, for example, something that LUX or LSET in the near future might be able to probe. If you go to germanium experiments, currently the bound for, or the threshold for super CDMS is about 0.35 kiloelectron volts. And you can see here that, again, we have no problems in principle to detect boron-8 neutrinos, other than we need a big size experiment. But also, this threshold falls very close to what you need to start probing CNO neutrinos, and that's actually quite interesting. If you were able to build a large tank of a very light element, for example, neon, and in this case, for example, there are spherical chambers that are being designed that can go down to energies, threshold energies of about 0.15 kiloelectron volts. You can see that you can actually explore, again, the CNO neutrinos quite well. The main challenge for these experiments is actually the size. These experiments are not yet, they don't have a large target, target material, okay? If you were looking for electron recoils, however, in all of these experiments, you can explore the whole range of neutrinos, which essentially means that the only thing that you're seeing are PP neutrinos. But that also provides complementary information that you can use, okay? Right, so what can we do with this information? So a little exercise that we did recently was trying to see what would it take for a direct detection experiment to observe CNO neutrinos. And the main motivation for us was the following, okay? All the neutrinos in all the fluxes have been measured. Essentially, Borexino has provided a good measurement for PP neutrinos, PEP, beryllium-7, and boron-8 neutrinos, with a small uncertainty, especially on PP neutrinos. Snow and SuperCamUcande have also provided measurements for boron-8 neutrinos. So in principle, we have those under control. CNO neutrinos have, however, not been measured. And interestingly enough, this is also related to the metallicity of the sun, okay? And predictions for CNO flux, in principle, depend on solar models and what we are assuming to as the sun metallicity. By metallicity, again, meaning all elements which are heavier than helium. Recently proposed low metallicity models are seemingly in disagreement with helioseismology data, and this has been given rise to two potential models for metallicity, a high metallicity model and a low metallicity model. And just for reference, I'm showing here how the flux of the neutrinos in the CNO cycle vary from the high metallicity to the low metallicity one, okay? You can see in principle that the change is quite significant, still difficult to measure, okay? So the challenge is not only to measure this population of neutrinos, but also to measure it with such an accuracy that we can distinguish between the high metallicity and low metallicity model, okay? So not only you need to see them, but you also need some statistics, all right? That's the main challenge. Right, so taking into account all that I said, what we've done here is to summarize what is the nuclear recoil energy, the minimal nuclear recoil energy that you would need for silicon, germanium, xenon, oxygen, neon, or helium target as a function of the events that you expect to find. The only thing here that you have to look at is where this becomes a plateau. So essentially, sorry, if you're looking for a silicon detector, which is this dashed line here, you would see that you would need a threshold of about, what is this, 10, 100 electron volts, which seems to be quite reasonable to start observing events. If you're looking at a xenon experiment, which is this dotted line here, you can observe that you're in the region in which you need a threshold of about 10 electron volts, which for these kind of experiments is completely unrealistic. And again, in my ideal experiment with a very light target, either helium or neon, you can see that these targets being very light, the threshold that you need is much higher, okay? So in principle, you're looking here at a couple hundred electron volts, which is quite reasonable given experimental sensitivities nowadays. The second variable is, of course, how big your experiment has to be to observe this. And this is what you can see here on the right-hand side. Again, with the same colors, I'm showing the exposure as a function of the threshold for xenon, germanium, silicon, neon, oxygen, and helium. And again, this is your ideal xenon experiment. Xenon experiments excel at looking for dark matter, but they are not going to be good for the purpose of looking for CNO neutrinos. Again, the exposure wouldn't be too big, but the threshold is unreasonably low. If you manage to build a very big helium detector, notice that this is about 1 ton-year exposure. That would be great, okay? But this is, so far, I think the technology is still quite far from here, from these kind of exposures. Again, I think a sweet spot would be germanium and silicon, which are this blue line and the gray line, respectively. You can see that with a threshold of about 20 electron volts, 30 electron volts, you can get there. The only problem is you need exposures of about 250 or half a ton year, okay? Super CDMS is far from that at the moment. The next phase is going to have 55 kilogram year, but that's something that can be scaled up, okay? So I think, in my opinion, regarding direct detection experiments, these are the ones that have more chances of seeing CNO neutrinos.
How low a threshold can it reach?
So, the only question here is how much energy you need, for example, to start observing events in germanium. Okay, the band gap there is, for example, 3 electron volts. You still need to drift the charge carriers to the size of the detector, so you're counting there on 10 electron volts, 20 electron volts. So that's quite reasonable, okay? I mean, it's not that easy, but it's quite reasonable. We've achieved those energies, okay? Obviously, neutrino detectors are also going to be looking for this. And in principle, if you look at SNOW+, 5-year running in scintillator mode, SNOW+ could also detect CNO neutrinos with the right statistics to distinguish between high and low metallicity scenarios. The main problem with SNOW+ is that if we dope it with tellurium in order to look for neutrinoless double beta decay, this provides a background that makes this kind of searches impossible, okay? Likewise, Borexino, in 10 years, could also achieve the same sensitivity if the bismuth rate is known to an accuracy of about 0.5 counts per day. So to me, it's an interesting race. There's obviously neutrino experiments are going to be good in looking for neutrinos, but quite surprisingly, dark matter experiments might also get there in the game quite early, okay? So far, this is, again, to me, this is quite interesting, and, but I've only been talking about standard model physics. And I think the title of the conference is somehow something related to beyond the standard model. So I thought I would be obliged to include something beyond the standard model. And obviously, it's going to be new physics in the neutrino sector, because this is what we're looking for here, right? What kind of new physics? Well, I'm going to assume that we have new mediators that appear in the scattering of neutrinos with either electrons or quarks, okay? We can think, for example, of a set prime model of B minus L, scalar mediator. I'm going to be completely agnostic about what the high energy theory is, and I'm going to concentrate on how this new physics would be observable in direct detection experiments. This is an example with a new vector mediator, and again, what this implies is that my calculation for the scattering cross-section of electrons or of nuclei has to be changed accordingly. In principle, for the electron scattering, you pick up new terms. Again, notice that in the denominator, you find the propagator of the mediator. So the lighter the mediator, the larger this contribution is going to get. And likewise, we also calculate the contribution for nuclear recoils. Interestingly, in the case of vector mediators, there are also interference terms, which can actually lower the prediction for coherent neutrino scattering that we had in the standard model. So that's quite, well, that's bad news. But in most of the parameter space, this actually means an increase. Right, so these are two plots for the standard model prediction, which is the dashed line here and the dashed lines in these plots, for the number of events as a function of the recoil energy, for electron recoils on the left-hand side and for nuclear recoils on the right-hand side. We focus on the case of electron recoils first. You can see that the contribution, with respect to the standard model, the contribution from new physics can imply an increase in the number of events at very low energies. The different lines correspond to different mediator masses, and the new physics contribution is larger as the mass of the mediator becomes lighter. Okay, so for example, this top line corresponds to a mediator mass of 1 kiloelectron volt, and as you increase the mass of the mediator, you regain the prediction for the standard model. Likewise, for nuclear recoils, you find the same effect. Again, a mediator mass of 1 keV implies a contribution which is larger than the standard model, especially at low masses. I'm showing here different nuclear targets again. Germanium is in red just for reference, and xenon is in green. Again, germanium, being a lighter experiment or a lighter target, can get a larger recoil energy much more easily. So again, given the fact that the detection experiments have not observed any exotic events, what we can try to see is how we can look for these new physics in the neutrino sector. And in particular, can we put new bounds, or can we put upper bounds on the corresponding couplings? And the answer is yes. All right? In principle, from the non-observation of exotic events, we can derive upper bounds on the coupling of the mediator as a function of the mediator mass, both for electrons as well as for nuclear recoils. In the case of electron recoils, we are not limited by threshold. Remember that any direct detection experiment is going to observe PP neutrinos. The only thing that matters is size. And therefore, to look for electron recoils, experiments such as xenon are going to excel. Xenon is very, very, very big. If you're looking for nuclear recoils, however, the threshold becomes the main issue. And in this case, for example, experiments such as germanium super CDMS, in which we have lowered the threshold to unprecedented values, are going to be extremely competitive, even with potentially better than big xenon experiments.
But if you were to find a signal, you would never distinguish it from one associated, say, with light dark matter.
That's a problem. I will come back to that in a minute, okay? For most of my talk, and this is a sentence I've always wanted to say, okay, I'm assuming that the background of dark matter particles can be disentangled. But if you don't, that becomes a very interesting question. Right, so how do these bounds look? I mean, this is not the first time we're looking for new physics in the neutrino sector, is it? How do these bounds look with respect to other searches? In this plot, I'm concentrated on the UV minus L model, and all these white areas corresponds to searches for new physics in the neutrino sector that have ruled out different windows of the parameter space. You can see here, for example, B physics. This is the coupling as a function of the mediator mass. So B physics is excluding some areas at heavy mediator masses. Searches like GEMMA and Borexino are excluding, neutrino experiments are excluding a big chunk of this parameter space. You also have solar and astrophysical probes, especially from cooling of supernovae and other stellar systems, that are also going to rule out some areas of the parameter space. All these bounds affect electron recoil scattering, and this is how direct detection experiments would be able to do in the future. As you can see, most of the area of the parameter space is covered, but still there is some window of the parameter space in which these experiments could still probe new physics with electron recoils. Again, this is in the particular case of the B-L model. If we didn't take into account bounds from electron recoils, but only considered bounds from nuclear recoils, many of these constraints are actually gone. We are left with bounds on the fifth force, fixed targets, bounds from supernovae, and of course the B physics bounds. It is in this kind of parameter space that direct detection experiments would provide a complementary measure, okay? And in particular, again, super CDMS, LUX, and future experiments are going to provide also some constraints there. Notice in particular, again, for example, that we are also covering this sweet spot of moderately high mediator masses with a not very small coupling, okay? So again, these experiments might be complementary to other searches. What this implies also, again, and now coming back to the interpretation of direct detection and coming back to your question, Jose, is that you might actually be in trouble. If we can explore new physics with these experiments, it might also imply that any future signal might be due to neutrinos and not dark matter. What this implies also is that the neutrino floor that I showed in orange before might actually not be sitting that low in cross-section. We have to re-derive the neutrino floor in order to take into account this new physics effect. And that's what we've done in the last work, okay? So what we've done is actually taken the highest possible value for the coupling of neutrinos to this mediator as a function of the mediator mass. And this is, for example, the case on B-L models. This line that you see here simply corresponds to this line here. So B physics constraints are here on the right-hand side. Fixed target constraints are here, and GEMMA and Borexino are cut in this region of the parameter space. Just for reference, the dashed line corresponds to the observation of coherent, which is also ruling out this area of the parameter space here. So if we consider that this is the limit of new physics in the neutrino sector, and you compute by how much the neutrino floor is raised, you find that, again, for helium, germanium, and xenon targets, the average increase is about a factor 2. That is not too much, and that only implies that you're only in trouble probably in the coming 5 years. Still means that you have to interpret your data carefully. Again, a factor 2 in the calculation of your background is not completely trivial. And in particular, for xenon experiments, it is already affecting the background calculations that they expect for boronate neutrinos. Just as a reference, the dashed area here corresponds to the area of the parameter space that is going to be probed by germanium experiments or xenon experiments. So both types of experiments are going to be sensitive to this moderate increase, which I think is quite interesting. Just to conclude also, we've done the same thing with a scalar mediator. And scalar mediators are slightly less constrained, and in particular, we've taken a lepton number violating model. We've been completely general with the couplings here, and again, we re-derived the upper bound on the neutrino coupling as a function of the mediator mass. In a very similar, well, in a completely similar analysis to what we did with vector mediators, what we did now was studying by how much the neutrino floor could be raised, and lo and behold, it's actually about 4 orders of magnitude higher at low dark matter masses. Okay? Helium experiments, again, germanium and xenon on the right-hand side. You can see here that the neutrino floor in the standard model is at 10 to the minus 43 centimeters squared. Taking into account new physics in the neutrino sector, it might be raised all the way up to 10 to the minus 39 or 38 centimeters squared for dark matter masses below 10 GeV. So this means that you're in trouble, and you're going to be in trouble in the coming years, not in 5 or 10 years. Okay? And this is actually, my point of view, really, really interesting. The neutrino floor can be orders of magnitudes higher than the standard model prediction. I'm going to finish here. Let me just say that this spectacular increase in the scalar sector is actually subject to the reinterpretation of bounds from from supernovae, okay? And this is something that we are doing now in collaboration with other people. Right, so I'm going to conclude here, okay? Direct dark matter experiments excel at looking for rare processes. They're going to be sensitive to coherent neutrino nucleus scattering in the coming future. And this opens up new possibilities to explore the sun a little bit better. As a little example, I was telling you, for example, that we can look at CNO neutrinos. It is challenging, but it might be done. And even more interesting, the neutrino floor might not be where you think it is. And this is cool. This means that new dark matter experiments are going to be sensitive in new physics in the neutrino sector. And it also means that we have to find ways of disentangling the neutrino floor from dark matter much earlier than we thought we would. Okay? Thanks very much. Yeah.
So thank you for a very nice talk. There are questions? Yes, Kim?
Yeah. If you try to constrain neutrino physics, why don't you consider neutrino magnetic moment? I was interested in magnetic moment a long time ago, actually. I'll show my paper. But if you want to constrain all this in detail, you must also give bound on neutrino magnetic moment irrespective of G prime.
Is that something we can also do with direct detection experiments in the same kind of thing? I believe that you're...
It is in fact Gemma, it's one of the
experiments.
experiments.
That would be, exactly, no? I mean, it would be cutting here, so
yeah,
it's
yeah.
one of those experiments.
It is.
That
It is there.
Any more questions? So this disentangling looks very interesting because it's a problem for dark matter detection, but also an opportunity for neutrino physics using coherent.
Yeah, it is a problem. We're trying now to address that in different ways within Super CDMS. And me and my student, for example, are using now machine learning tools to try to disentangle both. So it's actually quite cool. Yeah.
So one last question. Luca?
Can you just comment a bit on the directional dark matter detection? What do you expect in terms of neutrinos?
We can do that, yeah. So, I mean, the neutrino floor is not the end. Again, we were mentioning about how to disentangle it from a dark matter signal, and there are differences, okay? The first and obvious one is that the spectrum is not exactly the same unless you are a 6 GeV WIM with a given cross-section or a 100 GeV WIM with that cross-section, okay? So one first way of disentangling them is actually measuring the spectrum and then doing some spectral analysis, all right? Still, the neutrino floor is quite limiting there. The other possibility is looking for annual modulation. Both coherent neutrino scattering and dark matter signals are going to modulate, but for very different reasons. Neutrino signals modulate because your distance from the sun increases and decreases throughout the year. Dark matter signals are going to modulate because we are traveling the WIMP wind with different velocities. And finally, the one you mentioned is going to be the killer, right? That's directional detection. We manage to measure from where these scatterings are coming preferentially from. That would be great, okay? Neutrinos are going to come from the sun mostly, and dark matter is going to come from Cygnus. However, directional detection is still far away from the current sensitivities. Okay, that would be ideal, but it's still far away from current sensitivities. Collaborations such as Drift and Cygnus are going to look into it, and they're actually very interested. The last thing that they're looking at, and that's also why we provided these predictions, is because now they are looking at very light targets, and in particular helium and neon is very, very interesting for them. Okay, they are looking at very not dense targets. Obviously, they have to see the trajectory of the recoiling nucleus.
So let's close here. Thank again.
Thank you.
For a nice talk. Next talk, Constraints on Neutrino Physics from the CMB by Massi Lattanzi.
Thank you, Jose. Okay. Okay, thank you. So good morning, everybody. So first of all, let me thank Jose and the organizers for the invitation. It's always a pleasure to be here and visit this beautiful city, but above all, to see so many friends. So today I'll be talking about how you can constrain neutrino physics from CMB observations. So actually, neutrino physics is quite a big topic. So I will actually concentrate on some aspects, but let's go through that. So the most experts among you probably already know these things, but there are so many young people here, so I thought that it might be useful to recall just some basic facts about neutrino cosmology. So first of all, what we call the relic neutrino background is a prediction of the standard cosmological model, and it's a prediction that is based on the standard model of particle physics together with general relativity and basically the fact that we believe that we live in a Friedman universe, so a universe that started with a radiation-dominated phase at very high temperatures. So in this framework, you have that neutrinos are kept in thermal equilibrium with the plasma by weak interactions down to temperatures of 1 MeV. That means a redshift of around 10 to the 10. But then below, at 1 MeV, neutrinos decouple, okay? So they start to free stream. They don't interact anymore just because the universe is not dense enough for neutrinos to basically find one another or find other particles. And then you have that neutrinos keep the spectrum of a fermium at equilibrium. So if you extrapolate this to the present time, you have that today the universe should be filled with a background of neutrinos with a temperature of 1.9 Kelvin, which means around 100 particles per centimeter cube per species. So again, in this picture, you have just one free parameter, or at least in principle, you have 3 free parameters that characterize neutrino cosmology, which is the 3 neutrino masses. Actually, things are simpler than that because at least at the level of the present cosmological data, of the precision of the present cosmological experiments, you have that the cosmological evolution basically depends on the sum of the masses. Okay, so we have just one parameter. So how do you find out the MeV temperature? So it's basically a calculation that you can do on the back of an envelope. So precise calculation, of course, requires more care. But you can basically get the right answer simply considering that the weak cross-section that keeps the neutrinos coupled to the plasma is basically the Fermi constant squared times temperature squared. So the weak interaction rate is the Fermi constant squared times temperature to the 5th once you multiply by the density. The expansion rate during the radiation-dominated era is given by the Hubble rate, which is T squared over the Planck mass. And then you say that the interactions become ineffective when these 2 quantities are more or less the same. So if you do the calculation, you end up that this happens at around 1 MeV. So once you know that, you're basically fixing the neutrino density at a given time, and then you can just use conservation laws to compute the density and all other quantities just at any time during the cosmological evolution. So again, this is a prediction of the standard cosmological model, but do we observe those neutrinos? I mean, not directly, because these are very low energy neutrinos. I told you that they are at 2 Kelvin now, so they are roughly 10 to the minus 4 electron volts, so it's really hard to detect them, but we can see them through their indirect effect on the cosmic microwave background spectrum, because they gravitate, okay? So they contribute to the total energy density of the universe, and we parameterize these through this parameter, which is called N effective, which is the effective number of neutrino species, okay? And this is basically a measure of the energy density of radiation in units of the energy that you would expect from a single neutrino family. So of course, given the standard model, this number should be 3. Actually, if you do the precise calculation, and this has been done recently by Sergio Pastro and Pablo de Salas here, and previously by Sasha Dolgov and by, again, Sergio together with Giampiero Mangano and other people, you find that this number is slightly different from 3, it's actually 3.045, because basically neutrinos are not fully decoupled when the electrons and positrons annihilate, so you get just a slightly different number. So here I'm plotting the CMB power spectrum. It might look different from what you're used to see, just because I'm multiplying the spectrum by an additional factor of L squared, just to highlight the effect on this high multiple regime, which is what we call the damping tail of the CMB. So if I start from a model, which is the one in black here, with an effective around the standard value, and then a very effective, this is what you would see in the power spectrum. And the points here are the Planck measurements together with their error. And you see that, I mean, if you vary an effective, even basically by, let's say, 10%, the data should see that. And in fact, I mean, if you do the proper calculation, so you propagate everything to you do a proper statistical analysis, this is the most recent result from Planck 2018, plus BAO, plus the data on the baryon acoustic oscillations, and you get that an effective is 2.99 plus or minus 0.17. So you basically, the prediction is perfectly compatible with what we find from the observations. The error is quite small. It's still not small enough to appreciate the 3.045, but maybe next generation experiments might get down close to this, to the precision needed to see the difference. So this is somehow, I mean, you can think of this as a many sigmas detection, okay, of the cosmic neutrinos, okay, of the relic background of neutrinos. Because, I mean, if neutrinos weren't around, this n effective would be 0. Okay, so you see that we can say with some degree of confidence that neutrinos are out there, or at least that something that behaves like the neutrinos is out there. So I will come back to this in a while. So once you know that those neutrinos are there, I mean, you can use the data to constrain their properties. And of course, the first thing that you want to do is to see how massive they are. And also because in the standard picture, that's the only thing that you don't know from the cosmological point of view. And this is what you get again from Planck. So this is the sum of the masses versus the mass of the latest eigenstate. So these two curves are, of course, for inverted and normal hierarchy or ordering. And then, so this is what Planck tells you, okay? So this is the sum of the masses should be below 0.24 electron volts. So this is just Planck. If you add also the BAO data, so the BAO data help you because when you use just CMB, you have some freedom. You can kind of rearrange the expansion history in order to hide the effect of neutrino masses, okay? So you have some degeneracy. If you also use the baryon acoustic oscillations, you are kind of pinpointing some moments, let's say, of the expansion, of the cosmic expansion history, so you don't have anymore all that freedom to change the expansion history, and this, of course, improves your bounds, and in fact, the bound improves by a factor of 2. These are 95% confidence level bounds. So you see that the present bound is 0.12 electron volts. This is interesting because this is really becoming closer to, I mean, basically ruling out the inverted hierarchy, and also one might hope, and in fact, that's what we expect, that with next generation experiment, we might get down to detect the neutrino masses even in the, let's say, worst scenario case, which is the one in which the mass is, the hierarchy, the ordering is normal, and the mass is minimal. So this will be basically a talk by itself, and I won't talk about that, but I mean, we are very lucky because, I mean, we have both Maria Archidiacono that will tell us, as far as I understand, about future bounds, I mean, how future experiments might will enhance this, will improve these limits, and Isabelle Oldengott that will talk about something that I'm hiding here, that there is some amount of model dependence in this, in how, am I right? Are you talking about that, right? Okay. So, so which is how basically you, this is somehow model dependent in the sense that you are assuming lambda CDM, so you might consider a model with more parameters and your bounds might be weakened. And so again, we can hear what Isabel will tell us about this. Now, so as I was telling you, there are some assumptions behind all these, which are not. I mean, I don't think they are strong assumptions in the sense that they all come from the standard model of particle physics on one side, and from these. I mean, from general relativity, plus again the fact that we believe that the universe started at a very high temperature during the radiation-dominated era. But again, just to say that clearly, so all this assumes that neutrinos only have weak and gravitational interactions, so there is nothing beyond the standard model here, that there are no sterile, no right-handed neutrinos or any other light relic that might change the picture, that there is a perfect lepton symmetry, or at least that the lepton symmetry, the amount of lepton symmetry is very small, I mean, below our sensitivity, so this means there is zero chemical potential, that there is no entropy generation after neutrino decoupling and before plus or minus annihilation, that neutrinos are stable, okay? So basically this comes together with the fact that there are only weak and gravitational interactions, but again, in general, that there are no interactions that might induce processes like neutrino scatterings, decay, or annihilations, I mean, beyond what the standard model is telling us. But then again, you can play and you can see how, what are the extensions to the standard picture. So one is to introduce non-standard interactions that will affect the neutrino free streaming. This is interesting because this is not changing an effective, okay? So the total density will stay the same, but you will just have a different behavior at the level of cosmological perturbations. You can have a non-thermal distribution like in low heating scenarios, which is, so that means that your radiation-dominated era didn't really start at a very high temperature, so neutrinos don't have the time to thermalize, and this is a model in which you will see a smaller density than you would expect in the standard model. And again, we have, I won't talk about that, but we have been working on this with Sergio and Pablo. And you can have sterile neutrinos, so this means that you have an effective which is larger than 3, and you have another free streaming species, or you can have a large lepton asymmetry in which you have an effective, again, larger than 3, but also a larger average velocity of the neutrino. So the other interesting thing is that none of these model is can be exactly mapped in just changing an effective. Okay, they all have some additional effects. So here I will be concerned especially with the non-standard interactions, okay, and in particular I will talk about scalar interactions, okay. And so let's come to, before coming to the scalar interaction, let me tell you something more. So I was telling you that this is an evidence, okay, that you have a cosmic neutrino background. Of course, you might play the devil's advocate, no? In the sense, but are we really seeing neutrinos? In the sense that everything that behaves as radiation, okay, so whose density scales like the scale factor to the -4, will give you the same effect on the spectrum. Of course, you might be asking yourself, okay, I mean, you might, I mean, Occam's razor tell us that this is kind of not very probable, no? But in the sense that you need something that behaves like the neutrinos, that has exactly the same density that you expect from the neutrinos, but yet it's not neutrinos, okay? But still, let's see what if we can say something else that just say, okay, we have the right amount, we have the right density. So again, as I was telling you, you can look at the perturbations, okay? Because you might have different kind of species, okay, different species in the universe that behave like radiation at the background level, but they have different behavior at the perturbation level. So one thing that you can do, you can use there is a parametrization that was first introduced by Wayne Hu to basically describe what he calls generalized dark matter, and also Maria has been working on that. And so you basically introduce some effective sound speed and an effective viscosity in the neutrino fluid, okay? So you basically write down the equations for a fluid of massless particles with a viscosity, with an effective viscosity and an effective sound speed as free parameters. So what happens here is that when these two parameters squared are equal to 1/3, then that's basically neutrinos. Or if you want, it's massless particles, it's free streaming massless particles, okay? But you can also use, you can think that you have, for example, massless particles like neutrinos again, but that are not free streaming, but that are highly collisional. And then in that case, the viscosity will go to 0, okay? Or you can also think about more exotic things, like you have a scalar field that is oscillating in a quartic potential, and then the viscosity will be 0, and the sound speed squared will be 1. And then you can fit these parameters to the Planck data. This was done in 2015. and you see whether you recover the 1/3, okay? And this is basically what you do. So you recover the 1/3, I mean, within 2 sigmas, okay? So this kind of boosts our confidence that we are really looking at the neutrinos and not at something else. The only thing is that this parameterization is not really the most fit to describe non-standard interaction, because these 2 parameters are constant in time. Okay, so while if you have non-standard interaction, you expect that what happens is that during some part of the expansion history, neutrinos are non-collisional, while in some other part of the expansion history, they become collisional simply because the interaction rate is a function of the temperature. Okay, so usually you have the 2 regimes. And you cannot really describe the 2 regimes here unless you introduce some time dependence in these parameters. And also, I mean, using non-standard, using a different approach, it's also easier, makes it easier, as we shall see in a moment, to make a connection with the underlying particle physics. So here I will be, again, thinking about non-standard interactions, and in particular scalar or pseudo-scalar interactions. So with basically a Lagrangian that very sketchily contains this kind of terms. So these are mass eigenstates, okay? And there are basically 3 ways in which, I mean, there are many ways, but I mean, here I will just mention 3 and then concentrate on cosmology, in which you can constrain basically the coupling, okay, in this Lagrangian, okay? So one is with the supernovae, okay, and this gives you basically a forbidden region for the G's between a few in 10 to the minus 7 or 2 in 10 to and 2 in 10 to the minus 5, and of course this is the medium basis, okay? Then you have the neutrinoless double beta decay, because this will induce neutrinoless double beta decay, and then again you have an upper limit which is of order 10 to the minus 5 in the flavor basis. And then you have cosmology, in which you constrain the G in the mass basis, because you are looking, in cosmology, you are basically looking at the mass eigenstates. And this is so I'm spoiling the end of the talk, and the limit that you get is a few in 10 to the minus 7. Okay, so let's see how you can do this. Okay, so let me mention this is basically a work that I've been doing in Ferrara with Paolo Anatoli and Francesco Forastieri. Francesco is here in the audience, and also that this was part of his PhD thesis. And also this is a game that you can play in many ways. For example, you can consider vector-mediated interactions, or you can also consider how this works if you introduce sterile neutrinos. And again, we have also been doing that with Francesco, and also, I mean, Maria and Stefano here have been working on that. So, what's the picture here? So you have basically, I'm introducing a new scalar interaction mediated by a very light scalar. So this is important. Here I'm assuming that the scalar is very light. What I have in mind, of course, as a benchmark, and we will come back to that later, is Majoron models. So but this is more general than that. But this is what the typical kind of model that one has in mind when consider these kind of processes. So again, you can have this neutrino-neutrino scattering or neutrino-neutrino annihilation mediated by the scalar, and of course in the limit in which everything is, both the neutrinos and the mediator, is very light, the cross-section goes like the coupling to the force divided by the energy in the center of mass squared, and this is basically g to the fourth divided by the temperature squared. Okay, so this is the scaling with temperature and with decoupling. Of course, I mean, when you have in mind a specific model, of course, you have all the phase space factors and the symmetry factors, and then you get, for example, in Majoron models, you get 1/32 pi times g to the fourth over s. Then, of course, you can compute the decay rate, and you get this g to the fourth times t. And this is interesting because, I mean, the expansion rate, okay, basically decreases faster with temperature because it goes like t squared or t to the 1.5, depending if you are in the radiation or matter-dominated era. So the ratio gamma over h increases with time. It does not decrease. So usually with the weak interaction, gamma over h decreases with time. So neutrinos are coupled at very high temperatures and uncoupled at low temperatures. Here what happens is that when you go to very low temperatures, neutrinos become collisional again, okay? So since I don't want to stick to a particular particle physics model for the moment, I will just write the cross-section like some g effective to the fourth over t squared. So this is what you get for the interaction rate, and this is what you get for the, again, for the gamma over h. So this is the temperature of the universe. Time goes from right to left. So this is the standard picture where you have neutrinos that are, so when you are above 1 here, neutrinos are collisional, okay? So here neutrinos are collisional and coupled to the plasma, but then the cross-section basically goes, the interaction rate goes down, okay? And then you have that, so the standard picture, you just follow this line, okay? But if you add this extra interaction at some point, basically things change, the new interaction kicks in, and the gamma over h starts to increase again, and then at some point at low redshifts, okay, so from this redshift on, for example, if G effective is equal to 5 in 10 to the minus 7, neutrinos become collisional again. Note that they are not really coupled to the plasma because this is just an interaction among neutrinos, okay? So, but they become collisional again. So the whole perturbation evolution changes.
I mean, if this is to happen, your scalar, this mediator has to be super light, right? I mean,
yeah, I'm basically assuming that here I'm assuming.
But then, I mean, wouldn't that be just an additional degree of freedom during whatever PPN and so on and CMB? If that really happens, I mean, you have an additional light scalar which is just coupled to the neutrino, so it's equilibrated, and doesn't that just completely spoil early cosmology?
Not really, because I mean the point is that I'm assuming in some sense that that if there were any scalar in the early universe, it's been inflated away. Okay, but then but then again, I mean the cross section for the production of this guy from the plasma is very low because I mean if you extract, I mean it's basically this curve here, and this goes down. So the production rate of this guy at high temperatures is very low.
But you show that green line it goes up.
No, but the green line is the weak interaction rate. So this is the neutrino collision rate accounting for both weak interactions and non-standard interactions. If I were to put just the non-standard interactions, okay, this thing will basically go down like this.
Yes and no. I mean, if you do that game, of course, there will be also an effect on the temperature on this potential of this phi field because there will be temperature affected shifting.
Okay. No, we didn't look at those. Okay, yeah. So this is something to check. So, okay, so this is a little bit technical. So, I mean, if you write down the perturbation equation, what we are doing is that we are adding basically we are using the relaxation time approximation. So we are adjusting additional terms on the right-hand side of the perturbation equations. So again, this is what happens to the perturbation. So very quickly, this is the anisotropic stress at different scales. So what happens is that usually when neutrinos are free streaming, you have a large-ish, let's say, amount of anisotropic stress. But once you have non-standard interactions that make neutrinos collisional again, basically they are a perfect fluid, and the anisotropic stress is driven to 0. And this is, you see this in the difference between the blue, and the red curve. So the blue one is the standard case, red and green curves are two cases of interacting neutrinos with increasingly large coupling. So how this will look in the CMB power spectrum? So you have here that this will look like an overall boost of the spectrum plus a small phase shift that you don't see here, but you see in the residuals. Okay, so this is something that you can see from the data. You see something similar in the cross correlation between temperature and polarization. You see also something in the lensing. Lensing is something that is measured by Planck because you are basically making your neutrinos non-free streaming. Okay, so free streaming tends to decrease lensing. Okay, because you have less clustering of structures. But of course, if you add this interaction, you don't have free streaming, so you don't have this suppression effect on the lensing, and in fact you see that the lensing power increases if you go from the black to the red and then to the green curve. So finally, this is what you get from Planck. Okay, so this is that the coupling constant to the fourth is less than something like 3 in 10 to the minus 27 if you don't use the small scale polarization data. So if you take the fourth root, this is something around 10 to the minus 7, a few in 10 to the minus 7. If you add lensing, the limit increases a bit, improves a bit. This is what you can do with future generation experiments. Like this is for CORE, which is a satellite that was proposed to ESA, and the limit in terms of G to the fourth increased by 1 order of magnitude, basically. And as my very last slide, I was just to show an example of how this might be useful to model builders. Okay, so if you take a simple case in which you have this kind of scalar interactions is in Majoron models. Okay, so basically you have this Lagrangian in which you have a Dirac term for the neutrinos that is basically generated by the standard model Higgs. So you have right-handed neutrinos, you couple them with the left-handed leptons, and then you also can write a Majorana term for the right-handed neutrinos, and then you can put a scalar field here, which is the variant field of the Majoron. Then when the scalar singlet sigma acquires a web, it generates the large mass term that we saw in Ernest's presentation. But of course, this also introduces an interaction basically between the Majoron, which is the imaginary part of sigma, of the singlet. So you end up with this kind of Yukawa Lagrangian, and so this is the coupling, which is proportional to the neutrino masses divided by the web of the singlet. So you can also write everything in terms of the webs and of the Yukawas. And then basically, if you use the upper limit, that G should be less in 10 to the minus 7, basically you can say that these, you can somehow constrain the parameters of the Lagrangian. So you have that this combination of the web and of the Yukawas should be larger than 300 TeV. So I'm done. This is my summary, but I will leave it here. Thank you.
Sorry, we are in a hurry because there is a guided tour just after the coffee break. So if you want to get coffee, we should rush. So just one question for Massi, and then we can. Is there any question?
Now that you say that.
Now that I say that, there will be no question. So let's do it over coffee. Thank you.